In this example, we will improve our handwritten digit recognizer, which we have implemented in week 2. We will use a convolutional neural network for this. Remember, in week 2 we have used softmax regression in TensorFlow and got an accuracy of around 92%. So let's see if we can do better. We will start with a couple of imports. Again, most of the frameworks are providing the most interesting datasets as imports. So in this case we will use the MNIST dataset provided by Keras. We will use the already known sequential model type and we import 3 layer types. Dense, we already know what it is. So dropout, which is a functionality to prevent overfitting, is usually only a parameter to a layer, but in Keras it is modeled as a separate layer. Since deep learning is anyway nothing else than stacking functions, this perfectly makes sense. So how dropout works is that during every iteration a number of random neurons gets freezed and the weights are not updated. So this prevents overfitting and the model generalizes better. Flatten is a layer which reduces the dimensionality of a tensor, which we will see later. Then we imported 2 important layers for convolutional neural networks. Conv2D is a 2-dimensional convolutional layer which perfectly fits image data. And max pooling 2D, as the name suggests, is a pooling layer using the max pooling function, again in 2D. The pool shape we can specify later. Keras allows us to access properties of the underlying backend with a special function. In this case, we can access those functions using capital K. We are defining some constants. You should already know what those mean. Then we define the shape of the images, which are 28 by 28 pixels. Note that in this example we are not using a vector of 784 pixels, but the 3D tensor of 28 by 28 by 1. The third dimension usually is reserved for the color value and has a shape of 3. Let's load the data. This is a very convenient method because it returns a tuple of 4 NumPy arrays. We have the input vector to the neural network with a size of 784 and we have a target vector with a dimension 1, which contains only the class labels from 0 to 9. And it also returns a split between training and test data. Now it's time to access the properties of the TensorFlow backend by using the K variable. Since other frameworks are also supported, we have to define the way how the color information is encoded in the image. So in case of Theano, it would expect a 28 by 28 by 1 tensor, but here we need a 1 by 28 by 28. We have only 1 here because it's a monochrome image and not a color image. We apply some data preprocessing by casting the data and normalizing it. Normalizing is straightforward here. We just divide by 255 and we obtain a value range between 0 and 1. We do some prints in order to verify if the shape is correct and also to count the number of training and test examples. So since the label is encoded as a single dimension with variables between 0 and 9, we transform this to one hot encoded vector using the Keras 2-categorical function. We start with a sequential model and add a 2D convolutional layer. This layer has 32 neurons and uses a 3 by 3 matrix to scan over the image. We are using ReLU as activation function and we define the input shape as 28 by 28 by 1 because we are using the TensorFlow backend. This is followed by another 2D convolutional layer, but this time we are specifying 64 neurons. Followed by this, we are adding a max pooling layer, a 2D max pooling layer, which is scanning the image by a 2 by 2 matrix. Now we drop out 25% of the neurons in each iteration. Now we flatten down the 28 by 28 by 1 tensor into a vector of 784 elements, and then we add a fully connected layer with 128 neurons. Again we drop out, this time 50% of the neurons in each iteration. Finally we end up with a fully connected layer with 10 output neurons. Note that we changed the activation function from ReLU to softmax, which is an ideal fit for a 10 element one hot encoded vector. As cost function, we define categorical cross entropy, which is a very good fit for a multi-class classification task. As gradient descent updater, we use adder delta, which turns out to converge best given the dataset and that neural network topology. Then we start training with the usual parameters. After training, we check the accuracy using the test dataset. Finally, we print loss and accuracy on the test dataset and we are done. Let's run this. After training with 60,000 examples, we notice that we are doing quite well on the training data. And if we look at the test data, we see that we are doing an amazing job. We went up from 92% accuracy with softmax regression to 99% accuracy using this very simple convolutional neural network. In the next video, we will see how a more complex convolutional neural network can give us amazing results in image classification.